When doing Riemann sums, there are a few series formulae that you use over and over again. They're given to you in your information booklet in the exams. But I know some of you might be thinking, where do these formulae come from? And even though the proofs are not examinable, I'm going to give you the proofs of the first three, leaving the last one for you to maybe try on your own, just so that you can have an idea of where they actually come from, just in case you're wondering why. So the first formula that we deal with in the Riemann sums that we use is the fact that the sum from I is equal to 1 to n of 1 is n. Now this proof is quite straightforward. Okay, so if I am summing up I equals 1 to n of 1, that just means I've got n ones. So I've got 1 plus 1 plus 1 plus 1, and that there are n of them. There are n terms. Okay, so that's n times 1, which just gives me n. So that's why we get n as our sum. So that one's quite straightforward. Let's look at the next one. All right, so the sum from I equals 1 up to n of I. This is basically proving the formula for the sum of the first n positive integers. So I'm just going to write a few of those out. So we know that the sum, let's actually just write it out here. This is actually what we're proving. The sum from I is equal to 1 up until n. That means 1 plus 2 plus 3 all the way up until n. Gives me n times n plus 1 over 2. So that's actually what I'm proving. Now, this proof comes from, it can be done using mathematical induction, so you can try that yourself, but I'm choosing not to use that proof today. So the method I'm going to use is actually used by a German mathematician, Carl Friedrich Gauss. And he did this proof when he was only 10 years old. And it uses a little trick. So we start by writing the sum. We're going to call the sum S. We're going to start by writing it twice. Once in the usual order and once in reverse order. So we're going to call our sum S. And we're going to write it in our usual order. That's 1 plus 2 plus 3 plus dot 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 all the way up to n. Let's put in the term before, which is n minus 1, plus our last term, which is n. So I've written out my whole sum. Now I'm going to write it again, but in reverse order. So I've got n plus n minus 1. If we go one less than that, let's pop that in. That's n minus 2. All the way to my first two terms, which is 2 plus 1. So I've written my sum out twice, once in normal order and once in the reverse order. Now we add all the columns vertically. So I'm going to add that, I'm going to add that, I'm going to add that, which I can do because I'm adding both my sums. So if I add them vertically, I'm going to get 2s. Adding those columns, 1 plus n gives me n plus 1. Here I'm going to add 2 plus n minus 1, which again gives me n plus 1. Here I'm going to add 3 plus n minus 2, which again gives me n plus 1. Here I add n minus 1 plus 2, which again gives me n plus 1. And the last one, n plus 1 again. Now on the right side, there are n terms. Okay, so because we added up our columns and we know that there are n columns, we're going to land up with n terms, and each of our terms is n plus 1. So I can simplify and say, well, 2s is equal to n times n plus 1. Now I want s, I want my sum. as the subject of my formula, so I divide both sides by 2. So therefore I get that my sum is equal to n times n plus 1 over 2. And what is my sum? Well, that is what I'm looking for. That is my sum. So I've proven what I wanted to prove. All right, let's look at the next one. Here I am proving the sum of the squares of the first n positive integers. So if I write that out, let's just write it out, see what it looks like. So I'm proving 1 squared plus 2 squared plus all the way up to n squared. And I'm proving that that is equal to n times n plus 1. So we could squash it in here. 2n plus 1 over 6. Now I'm actually going to show you 2 different ways to prove this. One is by using a telescoping sum. Now you may not have come across this before, but it's quite a nifty little trick almost. So the important thing is that we're going to let S be our desired sum. I'm actually going to write that in another color. Let S be the desired sum, just like we did in the previous one. The desired sum. All right, so we're going to start with a telescoping sum. It's also known as a collapsing sum. Now you might think, geez, I would never have known to do this, but it's the first time you may be seeing it. It's a nice, nifty little trick. So I'll show you what a telescoping sum is. Now a telescoping sum, in this case, I'm going to go from I equals 1 up to n of 1 plus I cubed minus I cubed. So that's how we start our proof out, as a telescoping sum. Now, this just means that I'm dealing with I'm cubing it, and then this is just one more than I that we're going to cube. And you'll see how well it works out now. So if I had to write out the first few terms, if I make my I to be 1, this is going to be 2 cubed minus 1 cubed. So that means that my first term is 2 cubed minus 1 cubed. And we add, now I make my I to be 2. So I'm going to get 2 plus 1, which gives me 3. 3 cubed minus 2 cubed. Then I add, make my I to be 3. So I'm going to get 4 cubed minus 3 cubed. And I keep going until I get to, and I sub in n, and I get n plus 1 cubed minus n cubed. Right, now I'm going to show you why this is called a telescoping or a collapsing sum. Because most terms will cancel in pairs. Can you see here that I've got a 2 cubed, and I'm going to be minusing 2 cubed. Here I've got a 3 cubed, and I'm going to be minusing 3 cubed. Then the 4 cubed will cancel with the next term. The only one that didn't cancel in this case is that minus 1 cubed. Keep going, and you will see that this n cubed would cancel with the one before. So if I had written in that previous term, see that the n cubed cancels. Now the n plus 1 cubed doesn't cancel because I don't have a term afterwards. So after everything collapses, because I've been able to cancel, I'm then left with, I've got that negative 1 cubed and I've got the n plus 1 cubed. I'm going to write it with the positive 1 first. So I've got n plus 1 cubed and I've got a negative 1 cubed. If I times that out, now I'm not going to go through the whole process of timesing n plus 1 cubed out. It's actually, let's look at it. It's quite a long process, but we can do it. If you've got a short method for timesing out n plus 1 cubed, you can do that. Otherwise, you can go n plus 1, and you're timesing by n squared plus 2n plus 1. I've just squared it. then I've got my minus 1, times that out, you've got n cubed plus 2n squared plus n squared plus 2n plus 1 minus 1, and you'd end up with n cubed plus 3n squared plus 3n. All right, so that's what we get when we work with our telescoping sum. Now, on the other hand, we can also do our telescoping sum. We can also do the sum, in another way. So we know that also, if we do our sum, let's do it again. Exactly the same sum. 1 plus I cubed minus I cubed. Identical sum, I can times that out. Now we know from timesing n plus 1 cubed minus 1 cubed that we get n cubed plus 3n squared plus 3n. If I times that out, and you can try it, I'm not going to go through the whole process now, but if I times that out, I would get 3i squared plus 3i plus 1. So you just go through the process of timesing that out. Okay, now we know that a sum can be split over different terms. So this is the same as, and we can take out constants. So it's the sum of 3i squared, which is 3 sum I squared plus 3 sum I plus the sum, let's just rub that out, plus the sum of 1 up to n. Okay. Now it's very important to notice that this is what we're looking for, the sum of I squared. Now we know that we've called that S, so I can replace that with S because that's the sum that I'm looking for. So do you agree I can then have 3, and let's actually do that in red, 3S plus 3. Now we proved this previously, so we can use it. It's 3 times n plus 1 of 2 plus the sum of 1 up to n is n. Let's just simplify this a little bit. We're going to get 3s plus, times this out and simplify, you're going to get 3 over 2 n squared plus 5 over 2 n. So you can do that simplification yourself. So now we have two expressions for the same thing. So this is equal to that. Let's actually just circle it here in blue. It's equal to that. And the same telescoping sum is equal to that. Which means that we can equate them and solve for S. So therefore we have the first equation, which is n cubed plus 3n squared plus 3n is equal to this one, which is 3s, this S is the sum we want, plus 3 over 2 n squared plus 5 over 2 n. Okay, now we solve for S. If we get that 3s as the subject of our formula, we're going to get that 3s is equal to, and then we simplify, we're going to get n cubed plus 3 over 2 n squared plus a half n. Divide everything by 3. So S will be equal to 2n cubed plus 3n squared plus n over 6, because I've also simplified and put it over a single denominator. Factorize the numerator and you get n. You take out a common n, you factorize the trinomial that's left, you get n plus 1 times by 2n plus 1 all over 6. Let's go back and look. Is that what we wanted to prove? Yes, we wanted to prove that as our sum. So this telescoping sum is quite a nifty little trick where you find two expressions in this case, equate them, and then you can solve for S to find your sum. Now this wasn't the only way to prove this theorem. There is another way, and I'm going to explore that method as well. And that's proving it by induction, something that you are familiar with. So we're going to prove the same thing by reduction. Let's just rewrite what we required to prove at the top. So we got it in front of us. So remember that we are required to prove that the sum I squared, let's write out the first few, 1 squared plus 2 squared plus 3 squared all the way up to n squared is in fact equal to n times n plus 1 times 2n plus 1 over 6. Right, so let's remember how we do mathematical induction. The first thing is we prove true for n equals 1. So we're going to prove true for n equals 1. Alright, so if n is equal to 1, I've just got 1 squared on my left-hand side there. So I've just got that 1 squared is equal to 1. Cool. Then if we go to the right-hand side and we make our n to be 1, I'm going to have 1 times 1 plus 1 times 2 times 1 plus 1 over 6. Work that all out and I get 1. So the left-hand side is equal to the right-hand side. Therefore, it's true for n is equal to 1. Right, so next thing is we assume true for n is equal to k. Assume true for n is equal to k. Which means if I replace n with k, then I'm going to get that this is true. Then I'm going to get that 1 squared plus 2 squared plus 3 squared all the way up until, remember, we're substituting k in place of n, all the way up until k squared is in fact equal to k times by k plus 1 times by 2k plus 1 over 6. So I'm assuming that that is in fact true. Now I need to prove that it's true for n is equal to k plus 1. So I want to prove true for n is equal to k plus 1. Right, so actually what I'm trying to prove here, so I'm trying to prove if I add all of those together and I get up to k plus 1, it's equal to k plus 1 times by k plus 1 plus 1 times by 2 times k plus 1 plus 1 over 6. So I want to replace my n with k plus 1. So I start with my left-hand side, replacing my n with k plus 1, and I want to see if I land up with the right-hand side. So let's do that. So I start with my left-hand side. I've got 1 squared plus 2 squared plus 3 squared. And it goes all the way up to k squared, which is just before k plus 1 squared. So we end on k plus 1 squared. Now I know from the previous step that I know exactly what that is worth. that is this expression here. So I can replace it with that expression. So that's equal to k times by k plus 1 times by 2k plus 1 over 6. And I add k plus 1 squared. Alright, so now it's just going to be algebraic manipulation. So here I see that there is a common k plus 1 to both of these terms. So I'm going to take that k plus 1 out. And I'm left with k times 2k plus 1 over 6 plus k plus 1. Let's write this as one fraction. So there's my k plus 1 outside still. If I write this as one fraction, I've got k times by 2k plus 1. I want to get it over 6, so I need to times this term by 6. So it can all be over 6. Now I can go and times out these brackets here. So I've got k plus 1 multiplied by 2k squared plus k plus 6k plus 6 all over 6. Simplify. I've got k plus 1. Then I've got 2k squared plus 7k plus 6 over 6. If I factorize, I can now write everything over the same denominator. So I've got k plus 1. Factorize that trinomial and I get k plus 2 times by 2k plus 3 all over 6. And I'm so close because I want k plus 1 plus 1 and I want 2 times k plus 1 plus 1. So I can do that. I can rewrite this. So that's k plus 1. And instead of k plus 2, I'm going to write k plus 1 plus 1. Instead of 2k plus 3, I'm going to write 2k plus 1 plus 1. And if you times it out, you'll see that's just 2k plus 3 over 6. And that's exactly what I wanted to prove because this k plus 1 now sits in place of n. Because remember we had n times n plus 1 to n plus 1. So, therefore, I've proven it true for n equals k plus 1. Therefore, by the principle of mathematical induction, it is true for all, remember that symbol means for all, n is an element of natural numbers. So for all natural numbers, it is true. So I've now proven by mathematical induction that last series formula.